So we're going to start chapter 3, which is stacks. Let me load up the PowerPoint. But also, let's go ahead and just talk about something that you may not think we were going to talk about today, which is names. So naming and giving names to stuff is actually a really important thing because good names means you remember what everything is called. So let's go ahead and look at how bad we are at naming some things. 7-Year War. Fought between 1756 and 1763. Do the math on that one. 100 Years' War. 1337 to 1453. So basically there's some really, sometimes we're pretty terrible at naming stuff, or at least historians are, right? On the other hand, computer scientists, when we did stacks, we got it right. Stacks, we were really good at with coming up with stacks. So stacks are pretty easy to understand. They have 4 operations. They're really simple lists. Okay, they're like lists, but they're going to be even simpler. So we have 4 methods: push, pop, peek, and empty. Okay, that's it. And a stack is pretty straightforward to understand, the way the data structure works. Okay, so with a stack, you can imagine the metaphor I like to use, especially because I'm like hungry right now, is a stack of pancakes, right? And if you're trying to deal with a stack of pancakes, suppose you want to take a pancake off that stack. You don't go and just yank something out from the bottom. That's going to knock the entire stack off. You can't do that with with something from the middle. That's also going to like mess up the entire stack of pancakes and get that like maple syrup all over, and just it's going to be an icky mess. No, instead, when you're dealing with a stack of pancakes, you take the items off the top of the stack, right? You can only manipulate the stack from the top. Similarly, when we deal with like taking when we want to put something on top of the stack of pancakes, we only put it on top of the stack of pancakes, right? We can't like insert a new pancake into the middle of our stack of pancakes. That's, again, just going to knock everything over. Everything is going to go every which way. That's going to be terrible. That makes sense to everybody? Stacks are, so as you can see there, this is what, so everybody kind of understands that's how you manipulate stacks, right? You can only put stuff on top, and you can only take stuff from the top off. And that's literally how stacks in computer science work, right? You can imagine a stack. A lot of times a stack is drawn like this, or I'll draw it at least like this, where it's just kind of this open-ended thing, and we just throw things in. So the operation we call for putting stuff into a stack is called push. So we throw an item into the stack. Say I throw 1 into the stack, I push it into the stack, it's 1. If I put another thing on the stack, it's not going to go underneath 1. It can only go in from the top. So this next thing on the stack is going to be 2. Next thing would go in is there. And if I want to get something out of the stack, well, I only have 1 choice. I can only get 3 out of the stack. Okay? So that's what we call the pop operation. We pop it out off of the stack. Pop it off the top of the stack. And then if we popped again, we'd pop 2 out of the stack. So we push things onto the stack. We pop things off the stack if we want to get it. What if we want to look at the top of the stack without removing something from it? We call it a peek operation. So we peek at the top of the stack. So there's your 3 methods. Push, pop, peek, and empty. And anybody want to take a guess of what empty does? Sorry? It empties. Good guess. That's not what it does, though. It's better. It should be better. It really should be called isEmpty, right? To check if it's Boolean, right? So it checks. So empty just returns true or false. Instead of keeping track of the size of the stack, we don't bother keeping track of the size. We just check, is the stack empty or not? Okay? That's it. That's really all a stack is. Now, just like a list, you can use an array or a linked list to implement these things. Now, I'll probably use a linked list because that's pretty easy to do. But as it turns out, stacks are basically the most fundamental data structure in computer science, by which I mean if you give me 2 stacks, I can basically build a computer out of it because basically you can use 1 stack to hold all the bits to the left and 1 stack to hold all the bits to the right. And then I can simply move between the bits and add new bits on and take bits off. And that's all you need to simulate a computer. Yes?
So you can't look
You can look. You can only look at the thing that's on top of the stack. That's all you can do. You can only look at what's on top of the stack. That's it. Then you can also only tell if it's empty or if it's not empty. That makes sense? Okay. So the other metaphor that I hear besides pancakes, which is also food related, more candy related, which is Pez Dispenser, which you know, most of you should have heard of, and if you don't know what that is, then it must be only an American thing then. Okay. But a Pez dispenser is these like little. Here, let me go ahead and look it up for the people, because there were people in my previous class last semester who did not know what a Pez dispenser was. So Pez dispenser, right? Images, and hopefully this won't backfire on me. These things, right, where they've got characters on there, and you load candy, you pull it out, you load candy in, and when you open up when you open it up, it spits out one, right? You can load it up from the top, right? You load in the candy from the top, and the first thing you put in is going to be the candy at the bottom, right? And then you get and then if you open up like this, it will dispense the topmost piece of candy, okay? Right? So we have a term for this called LIFO, last in, first out, right? So last thing you throw into the stack, it's going to be the first thing that comes out of the stack, okay? Some people like to prefer it as like the FILO, like first in, last out, but they go with LIFO here. So only can access the top item, only get one item at a time. And again, these are the 4 methods that you have, and we've already went through them. You can check if the stack is empty. You can look at the top element. You can remove the top element and return it to you. Okay. So, and the other one, this last one, you push the element on top of the stack. Make sense to everybody? Okay. Fairly straightforward, right? So say we've got these 5 names: Jonathan, Dustin, Robin, Debbie, Rich. Okay. So we would say that basically, since John, right, and we look at these like from top to bottom. So Jonathan was most recently pushed onto the stack, and Rich was the very first thing pushed onto the stack, right? So it's at the bottom. Rich is the oldest. Jonathan is the newest. So if we were to look at, if we do peek on the stack right over here, we get Jonathan back. If we pop, we get Jonathan, and now we end up with this thing, right? With the stack at B. And now if we were to push Philip onto the stack, well, now Philip is the top item of the stack, right? Very simple operations. There's nice and unambiguous, which is why we like stacks so much. So you might be going like, okay, it's a stupid list. Who the heck cares, right? And that's actually an excellent question, like who the heck cares? Well, it turns out that stacks are like ridiculously powerful at what they do. Like they are absurdly powerful. And because of the limitations, they're easier to use than lists. And you can write some very powerful algorithms with stacks. In fact, a lot of the times when we get into recursion, if you don't want to use recursion, you'll want to use a stack, because stacks are fantastic at backtracking. But let's look at a very obvious and fun application. First is finding palindromes. So this is typically an assignment I give out, and I might not give it out next week. But let's see what I might give out a new assignment for stacks. I got to find out one, but this has typically been a previous assignment in semesters. So a palindrome is one of those words that you may just not have known the word for, which is it's the word that in English that's spelled the same forward and backwards. We ignore the case and we ignore the punctuation for palindromes. So kayak. So see how kayak is spelled forward to backwards the same. I saw, I was I. So notice how basically that's spelled the same forward and backwards. Okay. Able was I ere I saw Elba. Right. That is spelled the same forward and back. Level, madame, level. Right. These are palindromes where basically all the letters are the same. Now, if we want to keep, anybody know any other palindromes off the top of their head? Race car. Race car. Wow. Sorry. What was that one? Wow. Wow. Yeah. Madam, I'm mad. Adam. Madam, I'm Adam. Okay. Yep, that's another one. So we have to ignore the apostrophes there, where normally I do. My personal favorite is a man, a plan, a canal, Panama, which is a palindrome. So these are, so when somebody can come up with a nice palindrome for a headline, like it's one of those really fun things that happen sometimes. So a common problem is write a string that, so let's see how could we detect palindrome using a stack. And it should be fairly apparent by the problem. We want to spell something the same forward and backwards, right? So how can we do that with a stack? Let's just think about it, not even get into code. Let's just think about it theoretically because it's a pretty trivial problem. Let's take each character and push it into the stack, right? So to test whether or not kayak's a palindrome, we take each letter, throw it into the stack, okay? And what is that going to do? That's going to put the first letter on the bottom and the last letter on top, right? And now if we read the stack, it's going to come out in reverse. And so now we just check, okay, does it come out, if it comes out of the stack, is it the same word that I pushed into the stack, right? So I would check, does K match the K in kayak? Does A match the second letter? Does Y match the third letter? Does A match the fourth? And does K match the fifth letter, right? Yes?
Would you use peak instead of pop?
No, well, the reason we want to use, I mean, you could use peak first, but you're going to want to use pop anyway because you want to get to the next letter, right?
Yeah.
Right? So, so let's go ahead and see that on a case where that doesn't work. So let's go ahead and say we want to test, let's see, I'm trying to think of a word that doesn't fail immediately. So something that starts and ends in the same letter. Let's see, and a lot of them, I think that pop into my head, of course, are palindromes. Let's see. America. So let's go ahead and just convert it all to lowercase because we want it to be basically as simple to choose. So we throw America into the stack. A-M-E-R-I-C-A. The first thing we do is pop out A and check is that the same as the first letter. Okay? It is, so we're going to continue. Pop out C. C versus M. They don't match, so it's not spelled the same way in reverse as it is in going forwards. So see how this is a pretty trivial operation that you can just do right here. Doesn't require any anything extra. I mean, we could have done it using a list, even a doubly linked list, just by iterating through it first and back. But that would have required a lot of overhead. The stacks is pretty simple. All you had to do is just take every character, push it into this stack, and then run a loop. While this is not empty, pop the stack and check it against the ith character. Right? So the other thing though is that I find very interesting is the balanced parentheses problem. So checking to see whether parentheses are balanced, it's actually not that easy. Like one of the big things, if you've been doing a bunch of the extra credit and looking up regular expressions, and if you've decided to play around with them on a weekend, like I suggested, you might have found that they had some limitation. And basically, one of the big limitations of regular expressions is the ability to match parentheses, right? Which is to check basically, are expressions balanced? Can we balance out these parentheses, right? Basically, do each of these open parentheses have a closing parentheses in the appropriate place? That's what I mean when balanced parentheses, right? Does the expression work, right? So that's an example of one that does work. So let's look at an example of one that doesn't work, okay? An example of a parentheses that doesn't really work. Let's see. And this is hard for me to do because, if I see unbalanced parentheses. Okay, so this is an example of unbalanced parentheses, right? Where we have an open but not a closed, right? Technically, this is balanced, right? It doesn't really say anything to us. But also, right, this is unbalanced, right? We've got a closed and an open. That's not going to work. Does that make sense? You've got a closed and you've got an open, even though you have the same number of opens and closes, right? They're not in the right order, so it's not really something that can really be easily detected. And you can't just come up with a rule like saying, oh, all the open parentheses come before all the closed parentheses, because it's not that simple, right? Sometimes we do something like this. A plus B, right? C, C plus D, over here, and then so we have here we have an open, a close, and an open, right? So the open and so the close before the open is fine over here because we've got an open over here, right? That's perfectly fine. So how do we tell a computer to do this? How do we even get through this problem? Well, it turns out that can use stacks in a very interesting manner to solve this problem. It's kind of crazy, actually. The idea here is, and they point out that this gets even worse if we were working in computer science, actually, because in computer science, we might have something like this: multiple types of parentheses, right? Brackets, right? So that's going to make things messy, but we'll build up to that. It doesn't take much to build up to it. But the idea here is that we're going to use stacks, okay? And the idea here is they go into a bunch of code detail. Like they create a method to say, okay, let's write a method that says, is this string balanced? Return true if it's balanced with parentheses, or false if it's not. Check whether a character is an open parentheses or a closed parentheses. So all we really want to do with this, the idea here, is that every time we see an open parentheses character or open brace character, right now we'll just think about open parentheses character, okay? We'll just go ahead and push that character onto the stack. We'll ignore all the other characters because if we're just counting parentheses, they don't matter, right? All we care about are do the open and closed parentheses balance out, okay? We don't care if it's a valid expression or not. We just need to make sure the parentheses match, okay? So anytime we see an open parentheses, we push it onto the stack. Anytime we see a closed parenthesis, what we're going to do is we're going to pop the stack, okay? And we're going to make sure that basically that the open and the closed, they match. So basically, if we push it in a parenthesis and we see a parenthesis and we pop it out, we've got a parenthesis and a parenthesis. And we'll see what that means with regards to the when we get into the dealing with things that aren't parentheses. So here we've got, right, we go to this expression, right? We've got the open parenthesis, we've got a bracket, closed bracket, and a closed parenthesis. So we push on an open parenthesis, then we push on the bracket, okay? Then we get to the bracket, and so here we pop off. And now we're going to ask, is this a closed, this was a closed bracket, so did I just pop off an open bracket? If I did, it matches. That makes sense? Right? And now we go over here, we pop off a parenthesis. And if we get to this parenthesis and we popped off a parenthesis as opposed to a bracket or a curly brace, then it matches. So if we get to this thing and it's all and we haven't shown that it's not balanced, then we assume it is. It works. Let's go ahead and look at something else a bit more. Or unless you want me to code this up and actually like write it. Yeah? Okay. I mean, got nothing better to do. We're actually fairly ahead in the lecture schedule, so spending time to understand this stuff better doesn't really matter. Okay, so evening stack. Now I'm not really going to like write the stack for us because it's actually using stacks are fairly trivial. They're actually fairly trivial to write. We'll get into them into that in a bit. Right now we're going to look on how we testing to basically learn how to use them right now. So let's first write that public is public static boolean, not boolean is balanced. Okay, and we're going to take in a string expression. Okay, and we're going to assume again when we're trying to decide something is something or not. The way we have to do a bunch of checks. The way I like to do this is that I assume one thing, and then as soon as I disprove it, I return the other. So here I'm going to assume the expression is balanced, unless proven otherwise. As soon as I'm proven otherwise, I can stop checking, and so I can return false. Okay, so what I need to do is that I'm going to use a stack. Okay, let's go ahead, and it's going to be a stack of characters. Hopefully that makes sense to everybody, since I'm going to be checking character by character, right? Okay, stack of characters, stack is equal to a, C is equal to a new stack character. And let's see, is the stack an interface or not? Let's go ahead and import it and find out. Nope, it is a actual class. And let's go ahead and look at the things that the signatures. It has it extends vector, which is a type of list, but push, pop, peek, empty. Well, actually, I can just, let me just go ahead and I can see what operations we have over here. Dot. So because it's a type of collection, the stack object does have a bunch of methods other than the 4 that I talked about, but that's just because of the way Java works with inheritance. But what defines the stack are just using those 4 operations. Okay, so first let's go with, so now we've got this expression, and what we're going to do is that we're going to read it character by character. So for, let's see, can we do an iterator character C in string, so in the expression. Can't do it like that, but what I can do is I can use the dot toCharacter array over here and turn it into an array of characters, and then use an iterator over that. So for every character in the expression, and this will go from left to right. Okay, let's go ahead and ask ourselves if C double equals, let's see, in open parentheses, or if it's an open bracket, or it's an open curly brace. And this is kind of how your computer is going to check to make sure that basically everything I'm writing matches up, right? Because remember, your IDE is a program. Somebody had to write it. Somebody had to write the function that checks to make sure that these 2 curly braces match, right? And then highlights that this curly brace is associated with this curly brace, right? It highlights that fact. Somebody had to write that. So this isn't just a make work problem. This is a problem that has actual real world consequences that improves like the productivity of so many programmers, you know, because you can easily look and make sure your parentheses are matching. Okay, so if it's an open parentheses, I'm going to push that character onto the stack. So if it's an open parenthesis, an open bracket, an open curly brace, I'm going to push it onto the stack. Okay? Else, if it's one of those characters, but it's the opposite. All right, so I'm just going to copy paste here. And then I'm going to flip it around. If they're the other ones, then I'll have to check them. So I'll come back to there. The other condition is else if it's anything else, right? I don't really care about that. So I can write continue there. Who here hasn't seen continue yet? Okay, continue. So how many of you know about break? Okay, break stops the loop dead in its track, right? It will just kill. If I put break here, it would just stop whatever it was doing. The loop would be over. Continue is kind of a weaker version of break. In fact, it's not really even necessary in this case. Continue just simply says, I'm done with this iteration of the loop. Go on to the next iteration of the loop. So I can actually leave it out over here, but it's just a useful. I just figured it was a useful time to bring it up. Continue just simply goes on to the next character in this case. Okay. Okay. So now the actual logic over here says, let's go ahead and make sure this matches. So if we so car top is equal to stack dot pop. So let's get the top character off. And now if top, so basically we need to check a couple conditions. The first, basically, if the top character is this thing, is a close parenthesis, then we need an open parenthesis. So if character is a, so if C is a top, sorry, so if C is equal to actually, it's probably better to split these up into 3. Else if C, so basically if C is equal to this, so first off, if C is a close parenthesis and the top is not equal to an open parenthesis, does that make sense to everybody? So if the thing I popped off doesn't match the thing that I just looked at, right? Then I need to return false. That makes sense to everybody? And then it's the same for the other conditions, only they're just the other types. Oh, and I should probably return false and not fillets. So if it's a bracket or a curly brace, so if I see a closed curly brace, I need a pop. So if I see any of these things first, I'm going to pop off. And then if I found that the character that caused me to pop off was a closed parentheses, and the top wasn't an open parentheses, then that means it's unbalanced, so I return false. If it was same with the curly brace. If I popped off because I saw a closed curly brace and the top isn't an open curly brace, it's not balanced. And that's all there is to this. So let's go ahead and test some expressions out and see what I mean. So system.out.println is balanced. So let's go ahead and see A plus B, right? Let's check our null case where we have no parentheses. True, okay. Running this one. Oh, open here, but no close parentheses. Okay, that works. But what about this, where I just have a close parentheses? Ooh, I get an error. Ooh, so I've got a bit much more to do this. Okay, so I've got more things here to do, so I've got to handle this case. So first off, how can I detect this? I get all the way to the end, right? If it's balanced, then there should be the same number of opens and closes, which means as a result, the stack would be empty. There'd be the same number of pushes and pops. So if stack dot empty, so if not stack empty, return false, right? If the stack is not empty, then it's not balanced. So now this should take care of that case, right? Still works for this case, where basically it is balanced. But what about this guy, where we got an exception? There was nothing in the stack and we tried to pop. All right, so else if the character, so let's go ahead and see here. So first off, if we reach any one of these characters, the error occurred here because we tried to pop because it was empty, right? It's not balanced. So first let's check to make sure if stack dot empty, if that's true, well, it can't be balanced, right? If it's empty at that point, then it can't be balanced. So we return false before we get to that, before we try to pop over there. So now it returns false over there. So great, we took care of the possible errors that can occur. A plus B. Okay, what about A0 plus, let's try something else. B of 1 plus like one of those 1068 final exam problems, right? Something like that, right? And that's actually, balanced because you've got the, you've got the parentheses matching over here, and this brackets. Oh, were we missing some? What did it return? False. Okay, so that was correct. True. Now it's fixed. So it works for these really complicated ones too. Even if we do like something like, even if we like throw some weird parentheses in these things, right? And it makes sense that we're basically, why do these have to match? Well, it's checking for this kind of thing, where I accidentally transpose these parentheses, where we've got the same number of the same types, but they're occurring in the wrong order, right? This isn't a valid expression. Right, that makes sense to everybody? So this is this is a fairly simple data structure that I was able to solve this very simply. All right, so how do I implement a stack? So we can use a array list, as you might imagine. They use a vector, which is just a global array of objects. And the way it works is that basically you can simply add it on to the end of the array, right? So we wanted this. So here's the thing about stack. It should probably be pretty simple to implement. And what I mean is that basically when we push something, that should be constant time operation. When we pop something, that should be a constant time operation, right? So, and then when we check to see if it's empty, that's obviously constant size operation. And when we return the top item, that's also constant time operation. All the operations for stack should be constant time. So if we're implementing it using an array, then the way to do that is to basically add it on to the end of the array, like adding on to the end of an array list. And the only time it might take more time is when we would have to double the size, right? For a linked list, it's pretty straightforward to see how this is a linked list. You just simply add it to the tail and then remove everything from the tail. Or add it, actually, no, you would add it to the head and remove everything from the head, right? For a linked list. You could add it to the tail as long as you were removing from the tail, remembering the tail was the top, and that kind of gets, or as they would say, the tail was the head. So that would get a bit complicated, right? So instead, we're just going to deal with, when we deal with linked lists, with a stack, let's just see how it would look if we were going to implement it in a linked list fashion. So this is the last thing we'll do. You'll find out that this is ridiculously easy to code up. So let's go ahead and create an actual stack. Okay. So the stack of items, right? I'm not going to deal with the head. I'm going to do top. So private. Oh, and we'll probably need a node class as well, right, to keep track of the next item. So private E, node E. We'll just simply have the private static class node E private, the same things we'd be using for a linked list. So private E item, private E next, node E next, and generate a constructor for it, which is, so can I generate constructor for, okay, yep, and generate a constructor, and we'll just, so it's the exact same thing as, as a linked list one. So let's go. So we have 4 methods to go through. First, the empty method, which I'll just call isEmpty instead. So public boolean is empty. All right. How do I check if this thing is empty or not? Any suggestion? Yep. Yep. Return top equal null. If this is true, it will be. If this is true, it will return true. Otherwise, it will return false. Right? That's all I have to do to check if it's empty. What about public E peak? How do I check the top? How do I look at the top item in there? Well, return top dot item. Right? Okay. Public E pop. First off, we need to just cause an error if this dot is empty, right? We can do a bunch of things. Here, instead of throwing an exception, I'll just simply return null. Okay? Okay. Otherwise, what I'm going to, right, should probably throw an exception there, like stack is empty exception, but I'm lazy right now, so I'm just going to return null. Otherwise, e to return is equal to top.item return to return, but now we actually have to remove the top of the list. How do we do that? Oh. Okay, and remember this, if we don't have a top item over here, this will also cause a null pointer exception. Sorry, a exception over here. So, e dot to return. So this isn't nearly as safe as the linked list one that I wrote. But anyway, if to return is equal to top.item, then top is equal to get rid of the top, we say the current top item is equal to the next item. Right? Top is equal to the item that comes after that. That makes sense to everybody? And then what about push? Public e push e item. It says for some reason I need to return the item I pushed in, so we'll just simply do that right here. I don't know why but that's what's specified in the API. So we will go ahead, and now that we're pushing an item, well, what we do is that we do node e new top, right? This item is going to be the new top of the stack. So new top is equal to new node item. And now same thing for we would do for a linked list, which is that we say that the new top's next item is the current top, and then top is equal to new top. Right? It's the same kind of thing as a linked list. So you can see that by learning how linked list works, this basically made us blaze through this part. Yes?
So we don't do new top dot next equals top dot item. It's just top.
Yeah, it's just the top, right? We're pointing to the next node in the list, not the next right. Yeah. Right. All right, so that's it. That's all we have to do to implement it like a linked list. So here the way they use that is that they basically put each item, on the end of the list as they push it on. Sorry, each end on the array, and if they need more space, they'll just get more space. And then here's the way I did it, which was a linked data structure. All right. So this is why we can blaze through it, because they're just simply stupider versions, or well, not stupider, but dumbed down versions of linked lists and array lists. Okay. In fact, Python doesn't even have stacks as far as I can tell. Instead, they just say use a list instead, and just append stuff to the end of the list and remove from the end of the list. Right, underlying array requires reallocation of space when the array becomes full. For linked data structures, that requires allocating storage for the links. But basically, because we're inserting deleting at one end, these are all constant time operations. So what else can we do? Well, stacks are how your computer does math. And I'll just simply briefly get into this and into this concept before we return on next Tuesday. But the idea here is that those Facebook memes that you see basically 95% of people can't get this simple math problem right, which is just simply it's all about PEMDAS and stuff. And the answer for that is because, first off, we have a computer, so we just plug it into the computer as written, right? But we don't want our computers to get into these Facebook fights about the proper way to evaluate stuff. So we don't have anything that has to be evaluated ambiguously. Instead, what computers do to do math is that they use something called postfix notation. So we write stuff in infix form, which is easier for us to read. Instead, what your computer writes stuff in is postfix, because it's completely unambiguous. It doesn't require any parentheses. There's only one way to evaluate it. For instance, 4, 7, multiply these together. That gives us 28. 4, 7, 2 plus times, that means that basically we need to add 2 and 7 together and take that sum and multiply it by 4. Now this looks really weird because you've got all these operations and it just happens to be different, but each of these can be converted into an infix notation. Yes?
So we write it as infix and the computer does it as postfix?
That's the easiest way for it to do it. I may be telling you a fib, but these are the ways that basically that are easiest for it to be evaluated. Right? This is how, how else are you going to figure it out? How does a computer, because this gets into the question, how does a computer know how to do PEMDAS? You got to make it simple, right? You got to make it a very simple program so it can, because you can't make it a very long problem, especially in the older days where we're limited to kilobytes of memory, right? There's got to be something pretty simple. So what are we going to do? So postfix notation is one of the easier ways to do it because it is unambiguous. And the way it works is that basically, as we get each number, we just simply push that number into a stack. Okay? And once we get to an operator, we pop 2 items off the stack, do that operation on those 2 numbers, and push the result back onto the stack. And that's all you have to do for this. So, we are pretty much out of time. So, it is 7:54. I think this is a good place to stop. And if anybody wants to come back to me with that actual answer of how computers do basic arithmetic, please come back with that answer. Okay?
There was something that's like really silly that I did.
All right. Give me a second to...
Yeah.
Let me go ahead and turn this off.